During this lesson, you will identify the Coulomb as a unit for electric charge. You will solve problems involving Coulomb's law and use vectors to represent electrical fields.
Now, there's nothing good on TV. Oh, hey, this looks like a good show. Hey, welcome back. In our first program on electrostatics, you learned that the simplest way to produce a static charge is by friction. But there are other ways to separate electric charges. You probably already know that just turning a television off and on can create a static charge on the screen. But did you know that you can use this static charge to help with the tough household chore of cleaning cobwebs from the ceiling? No, I'm not kidding. All you need is a helium-filled mylar balloon with a long string. Just touch the balloon to the TV screen to transfer its static charge by what method? Conduction is right. Then let the balloon float up close to the cobwebs. The polar molecules of the cobwebs will be charged by induction, so they will be attracted and cling to the balloon, and you can pull them down. Ugh. It's a good example of physics in action. Speaking of electrical appliances, I have a physics fact or fiction challenge for you.
Is this statement fact or fiction? Electrical devices will still operate if the third prong of the plug is cut off.
Well, this one is a fact, but with a catch. The third prong is called a grounding pin. Electrical devices will operate even if it is cut off. It should never be cut off, however. When this pin is plugged into the electrical socket, it makes a connection with a wire that leads all the way to the ground, probably through some metal pipes. This grounds the body of the appliance and prevents buildup of static charge on its surface, which could cause severe shock and injury. Large metal appliances and those with lots of moving parts will always have a three-prong plug. It would be very foolish and dangerous to break off the grounding pin. Now, when we say that something has built up a large static charge, what exactly do we mean? Physicists aren't satisfied unless they have something specific to measure and a unit to make the number meaningful. I feel some note-taking coming on, and I'm sure you feel some math coming on. Hey, we're both right.
In the study of mechanics, only 3 fundamental units of measure were needed to measure distance, mass, and time. To study electricity, we need to add another basic quantity and unit. We need to measure electric charge. The symbol for electric charge is Q. Some books use a capital Q, others use a lowercase q. Either one is fine. The unit for electric charge in the MKS system is the Coulomb. The unit is abbreviated by capital C. Remember that the units in the MKS system are pretty large. The Coulomb is also a large unit. 6.25 times 10 to the 18th power is about 6 billion electrons. You do not have to remember this number specifically, but you should know that 1 Coulomb is a very large charge.
Now that we have our new unit, we can use it in a law, which calculates electric force between 2 charged objects. Think about these 2 charged objects and try to think of 3 things that would affect the magnitude of the force between them. Don't worry about attraction or repulsion now. We just want the amount or magnitude of the force. Your teacher will pause the tape and come back when you have some answers. We'll get these down in your notes later. But first, let's see how you did. You probably thought of the first two factors that affect the magnitude of an electrostatic force between two charged objects. The first is the charge on each object. The second is the distance between the objects. And the third makes sense if you think about it. It's the material separating the objects. If the material is a good insulator, the force will be lessened because the insulator will shield one object from the other. Now, when we have several variables that affect each other, we usually have a law that puts everything together. This time, it's called Coulomb's law. Now, get this in your notes.
Coulomb's law looks like this. Copy the equation and make a note of what each symbol represents. F sub EL is the electric force. Q sub 1 and Q sub 2 are the charges on the two objects. D is the distance between the two objects. Notice this distance is squared. K is a constant, which depends on the material separating the charged objects. For air, K equals 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. This value will be given to you with the equation on every quiz and test.
Now, let's see if you can interpret the mathematical form of Coulomb's law. Use your math skills from first semester. Your teacher will give you this set of questions and time to answer them. Then, we'll go over the answers together. Local teachers, turn off the tape and give students problem set number 1 from the Facilitator's Guide.
Do you remember how to figure out how variables are proportional from the formula? The first thing you need to do is to get everything on one line. That means multiplying both sides by d squared. For number 1, we look at charge and force. They are on opposite sides of the equals, so when charge increases, so does force. They are directly proportional. Distance and force are on the same side of the equals, so when one increases, the other decreases. But be specific. Distance and force are not inversely proportional, but distance squared is inversely proportional to force. Now, for number 3, you need to think about what an insulator will do to the force between charged objects. Insulators decrease electrical forces, and you can see that K and F are directly proportional. So the better the insulator, the smaller the value of K. Finally, do you remember how to use the ones method? On this last problem, substitute ones for each symbol. Now, do what the problem says. In this one, it says that each charge is doubled. Put a 2 here and a 2 here, and the distance between them is quadrupled. So that's 4 squared. You can see that the force will be 2 times 2 divided by 4 squared, or 16. That's 4/16, or 1/4.
Well, there was nothing new in those problems, was there? The math skills you've already learned should serve you well for the rest of this year and beyond. Now, let's see how quickly you can answer this question. Here are 2 pith balls with the same charge. If we double the charge of ball A only, which ball will exert more force on the other? Tell your teacher. Many of you probably said that A would exert twice the force since its charge has been doubled. But let me remind you of a little something we call Newton's third law. A force, even an electric one, is an interaction between two objects. The force has been doubled, but it's the same for both A and B. You can't abandon the physics you learned last semester. Now, let's use some real numbers in an example problem.
What is the electrostatic force between two objects, positive 13 microcoulombs and negative 22 microcoulombs, which are 0.055 meters apart? First, you should notice that the units for both of the charges are a problem. They're in microcoulombs, and we need all the units to be in the MKS system so that they will cancel out and the force will come out in newtons. Remember that the coulomb is a very large unit. Well, in most situations, the charge on an object is going to be much less than a coulomb, so metric prefixes are used. The microcoulomb is the most frequently used, so we're going to have to convert it into coulombs. For that, we'll need a conversion factor. We'll use the conversion fact that 1 coulomb is 1,000,000 or 10 to the 6th microcoulombs. Now, since you'll have to make this conversion often, let me show you a trick. We need to divide 13 by 1,000,000 or 10 to the 6th. Since 10 to the negative 6 is the same as 1 over 10 to the 6th, we can simply put a 10 to the negative 6 at the end of the 13, and that will do it. Now, don't worry that this is not in proper scientific notation. Your calculator won't mind a bit, and it will put your answer in correct scientific notation for you at the end. Since we want to solve for force, the equation is already set up for us. All we have to do is plug and chug. Here's the unit and the number for K that will always be given to you. And now let's plug in our charges. Positive 13 times 10 to the negative 6 coulombs and negative 22 times 10 to the negative 6 coulombs. Our distance is 0.055 meters. Don't forget to square that. And don't forget to round your answer to 2 significant digits. The answer is negative 840 newtons. What do you think the negative means?
The sign tells you whether the force is attraction or repulsion. If both charges are positive, what will be the sign of F? Tell your teacher. F will be positive. And if both charges are negative, what will be the sign of F? It will still be positive. And if both charges are the same sign, what will the objects do to each other? They'll repel. So, a positive force means repulsion. And if the signs are opposite, one positive and one negative, what will be the sign of F? Negative. So, a negative force means attraction, since opposites attract. Now it's time for you to practice some problem solving. Your teacher will give you these problems and time to solve them. Then we'll go over the answers with you. Keep this in mind. The 2 mistakes most often made are using the wrong units and forgetting to square distance. Don't let it happen to you.
Local teachers, turn off the tape and give students problem set number 2 from the Facilitator's Guide.
In number 1, you must convert all the units to the MKS system. So we convert our microcoulombs into coulombs by using the fact, just like we did before, that 1 coulomb is 10 to the 6 microcoulombs. And that means we simply add this factor on at the end times 10 to the negative 6 coulombs. We also need to change 86 centimeters to to the MKS system to convert them to meters, we use the fact that 1 meter is 100 centimeters, and so we get 0.86 meters. Now it's just a matter of plug and chug. Here's our value of K, negative 14 times 10 to the negative 6, negative 22 times 10 to the negative 6 coulombs, 0.86 meters, don't forget to square it, and the force turns out to be positive 3.7 newtons. Include the sign even if it's positive so your teacher won't think you've forgotten it. For number 2, we'll have to rearrange the equation to solve for D. We multiply both sides by d squared to get it off the bottom. Then we divide by f and take the square root of both sides. Now we'll convert our microcoulombs into coulombs as we've done before. Our 6.4 newtons is in the MKS system, so it's fine. And the answer is 0.24 meters or 24 centimeters, which is a reasonable answer. For number 3, we want to solve for Q2. So we'll multiply both sides by d squared to get that off the bottom. Then we'll divide by K and divide by Q1 to isolate Q2. We'll need to convert our centimeters into meters and then plug and chug everything, and we get Q2 is equal to 4.0 times 10 to the negative 6 coulombs, or 4.0 microcoulombs.
If you're really a physics type, you may have noticed a similarity between this law and another law we studied last semester. Here's a hint. The law was named for a famous scientist who already had 3 laws and a unit named for him. I don't have any, but I'm not bitter. If you said Newton's law of universal gravitation, you're so right. Look at the 2 laws side by side and tell your local teacher what you find similar and different about the laws and the 2 forces.
The obvious similarity is that both laws show factors affecting forces. The force of gravity is always an attraction, while electrostatic forces can be attraction or repulsion. Both laws have a constant in them. G is a universal constant, never changing, while K depends on the material between the objects. Both multiply a vital property for each object, either mass, which influences gravity, or charge, which influences electrostatic forces. And both are inverse square laws involving distance between the 2 objects. If you double the distance between objects, the force in both cases will be divided by 4. Now, one big difference between the 2 laws is the values of the constants. Notice how large K is, 10 to the 9th, and how small G is, 10 to the negative 11th power. What does this tell you about the strength of electric versus gravitational forces? Tell your teacher.
Right now, I'm demonstrating what the constants tell us. You should have figured out that since the constant for calculating electrical forces is so much larger than the one for gravitational forces, electrical forces must be much stronger than gravitational ones. These pieces of paper are defying gravity because the electrostatic attraction is greater. Here's an even more dramatic demonstration.
Watch what happens when lightweight metal pie pans are stacked on top of the dome of a Van de Graaff generator. The pans become negatively charged by conduction, and the force of repulsion is greater than the force of gravity. The pans lift off one at a time.
Both gravitational and electric forces are called field forces because objects don't have to touch in order to be affected by the forces. For example, a gravitational field surrounds the Earth, and any object coming into this field will experience this force, whether it touches the Earth or not. Today, we'll look at an electric field, which surrounds any charged object. When another charged object comes into the field, it will experience a force. We draw lines of force to represent an electric field. Watch this, and then you'll take some notes.
To show an electric field, very thin fibers are suspended in mineral oil in this tank. Watch as a positively charged object is placed in the oil and the fibers align themselves with the field. This shows us the shape of the field in 2 dimensions. The strength of the field is shown by the spacing of the lines of force. The field is strong where the lines are close together and weak where they are further apart. Since electric forces are vectors, we also need to show the direction of the force. By convention, the direction of an electric force line is the direction a positive point charge would move in the field. So the arrows point away from positive and toward negative. Now you're ready for some notes. To draw an electric field, arrows are used to represent electric force lines. The arrows point away from positive and toward negative. The spacing of force lines indicates the strength of the field. The closer together the lines are, the stronger the field.
Let's draw the electric field around a positively charged sphere. We draw the positive charge and then draw arrows pointing away from the sphere, like this. To draw the field around a stronger charge, we would simply draw more lines, crowding them together, like this. Now, you draw the field around a weak, negatively charged sphere. This time, we draw the arrows pointing toward the sphere, and we only draw a few, showing that the charge is weak. Now look at the electric field between and around 2 spheres, one positive and one negative. Pay close attention to the force lines between the opposite charges. To represent this field, we draw curved arrows joining the 2 spheres. The arrows go away from the positive and toward the negative, like this. Finally, look at the electric field between and around 2 positively charged spheres. Notice how the force lines bend away from each other. To represent this electric field, we draw arrows away from both positively charged spheres. The lines between the 2 identical fields bend away from each other to show repulsion.
Drawing electric fields around small point charges is pretty easy, isn't it? But in real life, charges are spread out over a variety of surfaces. First, let's look at a large metal sphere, such as the dome of the Van de Graaff generator. Because electrons repel each other, they will spread out as far as possible. And this means that they will stay on the outside of the dome, where there's more room, not on the inside. In fact, the electric field inside the sphere is 0. And that's true for any conductor. Better get that in your notes.
All the static charge lies on the surface of a conductor. The electric field inside any conductor is 0. This means that a point charge placed inside the conductor would experience no force. Now here's a physics challenge for you. Is this statement fact or fiction? A car's rubber tires protect passengers if the car is struck by lightning.
It's the metal body of the car, not the tires, that protects passengers from lightning or any electric charge. The charge stays on the outside of the metal body, working its way to the ground, finally jumping to the ground through the moist air at the lowest point of the car, probably its back bumper. The electric field inside the car, where the passenger sits, is zero. Here's a dramatic demonstration of this type of shielding from the Boston Museum of Science. The scientist is protected from the lightning bolt produced by the giant Van de Graaff generator because he is inside a metal cage. This is called the skin effect, a type of electric shielding from the effects of moving charges like lightning or even current from fallen electric lines. The trick is to stay inside the cage, or your car. Now, here's a less dramatic example of the shielding of static charges.
For this demonstration, a PVC rod is rubbed with fur to give it a negative charge. When it is brought close to the top of an electroscope, the electroscope is charged by induction. But when a wire mesh cage is placed around the electroscope and the same charged rod is brought close, nothing happens to the electroscope. Any charge that is induced stays on the outside surface of the wire cage, and the electroscope is shielded.
Now, if the conductor is spherical, like this dome, the electric field is uniform. But if there are corners, the field will be stronger there. And if the conductor is skinny and pointed, like this copper wire, the field will be so strong around the end that the air in that region will become ionized. Since ions are good conductors of electricity, the air around a pointed conductor will form a conducting path to the ground or to a nearby cloud. Ever heard of a lightning rod? We'll talk more about lightning rods and lightning in our next program. But now it's time to show what you know. Your teacher will put the review questions on the overhead projector and give you time to make your choices. You'll go over the correct answers after this program ends. Here's one last way to show what you know. I'm going to do a demonstration for you, and I want you to explain the results to your teacher when the program ends. I'm placing some styrofoam packing peanuts in a plastic cup and placing the cup on the dome with the Van de Graaff generator. Watch what happens when the dome is charged. Now, I'll put some more peanuts in this metal cup and repeat the demo. Tell your teacher why the styrofoam pieces pop out of the plastic cup, but don't pop out of the metal cup. As always, try to use proper physics terms in your explanation. I'll see you next time.